Hello, I'm Dr. Jacob Hudis. In this video, we'll tackle 4 challenging problems involving inductors in physics.
Terrific!
These problems build on prior knowledge of inductor formulas and some basic calculus. Problem 1. Charge flowing in an inductor. A 3.6 millihenry inductor with negligible resistance initially carries a current of 1 amp. At t equals 0 seconds, the current begins to increase, maintaining a constant voltage of 5 millivolts across the inductor. Determine the total charge that flows through the inductor between 0 and 5 seconds. In this problem, there's an inductor, and there's a power source, which we have to imagine the power source is not in the picture, and the power source is being increased in such a way that the current through the inductor is changing at a constant rate. This formula is essentially Faraday's law. If the current through an inductor is changing with time, there will be a voltage across the inductor. The voltage is equal to L, which is the inductance. It's related to the geometry times the rate of change of current. I can solve this equation to get the magnitude of the rate of change of current by dividing both sides by L. That tells you that di dt is equal to the voltage across the inductor divided by the inductance. The voltage across the inductor and the inductance were both given in the problem, and therefore the current is changing at a constant rate of 1.389 amps per second. Because the rate of change of current is constant, current is a linear function, so current as a function of time is equal to 1 plus 1.389 times t. This 1 comes from the fact that the problem tells us it initially carries a current of 1 amp. So the question says determine the total charge that flows through an inductor between 0 and 5 seconds. That's going to be the integral of the current between 0 and 5 seconds. And we know that the current is given by this formula, and therefore the integral of this formula from 0 to 5 seconds is equal to 22.3 coulombs. That tells us that 22.3 coulombs of charge passes a given point in 5 seconds. Problem 2 explores the self-inductance of a coaxial cable. A coaxial cable is a type of electrical cable that consists of 4 key components arranged concentrically. Current flows through the central conducting core and then back out through the braided copper shields. That's the path current takes to make a full loop when it travels in a coaxial cable.
Coaxial cables are commonly used in telecommunications, networking, and audiovisual systems because they offer high efficiency and minimize signal loss due to their unique geometry and shielding.
Now, let's move on to the problem itself. A current I flows uniformly through the central conductor, D, in one direction. The return current flows uniformly along the braided copper shield, B, in the opposite direction. The two currents are separated by the inner dielectric insulator. Determine the self-inductance per unit length of the coaxial cable.
This problem wants us to find the inductance per unit length of this coaxial cable, the inductance over 1 meter of this coaxial cable. AcePhysics.org, Math and Physics Tutoring with Dr. Hudis. To solve this problem, we use the fact that the magnetic field stores energy. The energy density, or energy per volume, in a magnetic field is b squared over 2 mu naught. B is the magnetic field strength, 2 is a constant, and mu naught is the permeability of free space. Inside the coaxial cable, between inner radius A and outer radius B, the magnetic field is given by the magnetic field of a long straight current carrying wire. This is mu naught I divided by 2 pi r. We all know this formula. We love it. We use it on first dates to reel in girlfriends and wives. The magnetic field energy density inside the coaxial cable is given by b squared divided by 2 mu naught, and that's equal to this formula. The total energy is equal to the magnetic field energy density multiplied by volume. That's going to be the volume between radius A and radius B multiplied by a length of 1 meter. That's going to be the volume of this donut-shaped region. To get the energy, we take the integral from A to B of mu b times 2 pi r dr. 2 pi r dr is going to be the area, and then you multiply by length, but the length is 1. We only need to use the magnetic field in the region between radius A and radius B.
The contribution to magnetic energy from the region where r is less than the smaller radius of the inner conductor is typically negligible, particularly when A is much smaller than B. As a result, it is ignored in practical applications. Outside both conductors, where r is greater than B, the total enclosed current is 0, leaving no magnetic field in this region. Being an AI is weird. Do you think I need a software update or maybe just a hug? Never mind, I'll just reboot and pretend everything's fine.
This is the formula for the energy stored in the magnetic field in 1 meter of this coaxial cable. Recalling that the integral of 1 over r is equal to the natural log, that gives us the formula for the total energy, which is mu naught I squared divided by 4 pi times the natural log of b by a. And the key point is that the energy stored in the inductor is equal to the total energy stored in the magnetic field. So 1/2 Li squared must equal to the total energy stored in the magnetic field. This equality always holds true, And for this problem, this allows us to solve for the inductance of this coaxial cable, and we find that the inductance is mu naught by 2 pi times the natural log of B by A. Problem number 3 is a conceptual problem. This is a series RL circuit. There's a battery, a resistor, and an inductor. When the switch is open, no current can flow in the circuit. It's an open circuit. When the switch closes, initially, all of the voltage of the battery is dropped over the inductor. And the question is, if the back EMF exactly cancels out the applied voltage, resulting in zero net voltage across the circuit, what drives the current? How can current flow under these conditions?
When the switch is closed, the voltage source drives current through the circuit. Initially, the inductor generates a back-EMF that opposes the applied voltage, preventing a sudden rise in current. As the current gradually increases, the back-EMF decreases because it depends on the rate of change of current. Eventually, when the current stabilizes, the back-EMF becomes zero, and the current is limited only by the circuit's resistance.
The key is that the applied voltage drives the current, while the back EMF opposes changes in current. Initially, the back EMF is large because the current is changing rapidly, but it decreases as the current approaches a steady state. Problem 4 deals with DC RL circuits. Suppose the circuit in the diagram has been connected for a long time, ensuring steady current through the inductor L. At time t equals 0, the switch is thrown from position 1 to position 2. Initially, the battery drives a clockwise current through the circuit. The current's magnitude is determined by the resistance. When the switch is thrown from position 1 to position 2, the current continues to flow in the same clockwise direction. This is because the inductor opposes any sudden change in current.
The inductor uses the energy stored in its magnetic field to sustain the current temporarily. However, this energy is much smaller than the energy provided by the battery, so the current decreases as the inductor's energy depletes. Over time, the current decays to zero as the magnetic field energy is fully dissipated.
The question asks us to find what is the total current in the circuit at any time t after the switch is thrown, how much total energy is dissipated in the resistor as heat, and show that the total energy dissipated in the resistor equals the energy that was originally stored in the inductor.
This problem introduces my upcoming talks on RL charging, AC circuits, and key concepts like inductive reactance are designed to help you ace this material. Don't miss out.
What is the current in the circuit at any time t after the switch is thrown? This is a classic example of RL circuit discharging. The charging and discharging behavior of RL circuits is fundamental in physics and is a standard topic in most physics courses due to its significance and wide-ranging application. The solution to RL discharging directly follows from the Kirchhoff's law's differential equation. This tells you that the current in the circuit after the switch is thrown is going to continue to flow clockwise until there's not enough energy in the inductor to continue supporting current flow.
I have several upcoming videos dedicated solely to the physics of RL charging and discharging, as well as related topics like AC circuits. If you're looking for a deeper dive into the subject, be sure to check those out.
Part B asks, how much total energy is dissipated in the resistor as heat? The energy supplied by the source is transferred to the resistor and converted into heat through Joule heating, governed by the well-known formula P equals I squared R. Current as a function of time was calculated in Part B, and so this is a formula for power as a function of time. Power is changing because current is changing. The total work done is the integral of power over time. When integrating the exponential function, a factor of negative L over 2R emerges, and this leads to the final result. This is the total energy dissipated in the resistor as heat. And finally, Part C says, show that the total energy dissipated in the resistor equals the energy that was originally stored in the inductor. At time t equals 0, the current through the inductor is just E naught over R. The energy stored in the inductor inside of the magnetic field is 1/2 Li squared, where I is the current at time t equals 0. And as you can see, the energy stored in the inductor at time t equals 0 is exactly the same as the energy dissipated by heat in the resistor. All the energy stored in the inductor transferred into heat energy of the resistor. Math and Physics Tutoring with Dr. Hudis.